Thank you all for sticking for the last talk of the day. So I'm Samira Khan. I'm an assistant professor at University of Virginia. And today I will talk about how we should test persistent memory applications, what are the challenges, and how we can solve those challenges. So I guess I can actually skip the background stuff. We all know that we have these amazing non-volatile memory technologies where we can combine the characteristics of both memory and storage. And the benefit is now we have an opportunity to manipulate persistent data directly in memory. So it has a lot of benefit performance-wise compared to traditional storage device. But the challenge is what happens to all these system support that traditionally comes with the storage, our storage devices. And one particular thing that I'm interested in is crash consistency. So traditionally, file system is supposed to provide that support, so applications don't they don't have to do that much providing that guarantee. But now we want to avoid the microsecond latency in the switching the kernel, so that it doesn't overshadow the benefit of nanosecond latency NVM. And most of the industry and academic proposals have argued that crash consistency support should now come from the application. So that puts a lot of burden on the programmers that they actually have to provide that guarantee while they're coding their application. So this is the outline for the talk. So first I will talk about what are the challenges that programmers are facing where they are trying to use persistent memory. I will motivate that why we need tools that can help us to test and debug the applications. I will talk about our tool PMTest, which basically is a work done by my students and collaborators at UCSD and VMware. And I will finish with some results and summary. So when we are talking about crash consistency, there is two fundamental guarantees that applications need to provide. We need durability and we need ordering guarantee. So when I talk about durability, what I mean is the data from the cache, which is volatile, has to be written back to persistent memory to make it durable. And with the ordering, what we mean is there has to be some method which says that a write cannot move forward before the prior write has persisted. So basically, there has to be a write back, a barrier, and only then the next write can proceed. So now the programmers are supposed to provide crash consistency with these guarantees, but while they're actually writing their code. And there are two different ways now that we can do it. So one is for the expert programmers, where they will use these flash and barriers to write their code, but they need to have these detailed knowledge of both the hardware and also their algorithm. And there could be like regular programmers who will use a high-level interface so that they don't need to know all the details of the hardware and implementation. So first, let's see the first one. So basically, what Intel did is they have exposed all these hardware primitives for these flash and barriers. So instead of doing it the hardware, we have an efficient method to do it in the, instead of doing it in the software, we have this efficient method or instruction in the hardware. But the problem is ARM came up with their own instructions, and there are actually multiple proposals to optimize these fences, which most likely we will see sometime in the future. So there is a large variation on how we can provide the consistency guarantee using what hardware we are using. So let's see how we can use these flush and barrier instruction to just do a very simple appending just a node in our linked list. So this is a code where basically what we are doing is first we are creating a new node. Then we point the node to the current head, and then we switch the head to the new node. And remember that all these data is in the cache, so at the end there is a barrier and a flash, which makes sure that everything is persisted in our NVM. So is this code correct? It seems correct because they have flashed everything at the end, but actually it is not. So because the hardware can do all this reordering at runtime, it's not guaranteed that the head will always persist at the end. So there could be a case where the head persisted, but the new node has not been persistent in memory. And if there is a crash before the barrier, then we will lose this node, and essentially the linked list will become inconsistent. So the takeaway from here is the programmers actually have to know quite a bit about what they're doing and what the hardware is doing to provide this consistency guarantee correctly. So basically there has to be this extra barrier which makes sure that the head is persisted before we persist the new node. And in that case, even if there is a failure, we would be able to recover the linked list. So let's see what happens if someone is using the high-level interface. So basically, when I say high-level interface, it's more like a transactional library that Intel has provided through PMDK. And there are some more libraries available, but at the end, the backend mechanism is very similar. There is an atomic region where we have some sort of logging, redo, or undo logging, which will make sure the updates are committed atomically. So this is the same example where we are using a transaction to append a new node. So first, within the transaction, we create a node. We say that the head needs to be backed up for recovery. We update the head. We increment the length of the list. And the transaction ends. The transactional library makes sure that everything is logged and committed. But here, the length is not persisted. It's not backed up. And in the recovery, if we need the length to recover, and if we don't want to go through all the nodes to figure out the length, this has to be backed up. So even with transactions, we are expecting the programmers to know how the recovery code works or exactly what they're supposed to do in the transaction. So basically here, we actually have to add the length to back up, to log, and then we have a recoverable list. So even with transactions, there is a lot of burden on the programmers to understand what they're doing. So what we are saying that if it's so easy to make a mistake for the programmers, we should provide some sort of mechanism to the programmers so that they can actually test what they have done if that is matching to their expectation. And what should be the requirement of such a tool? So first, it has to be fast. It has to finish within some reasonable time, hopefully runtime, close to runtime. And the other requirement is persistent memory is being used in so many ways. So there are kernel modules or optimized file systems that are using these low-level library primitives. There are high-level transactional libraries. And also there are databases and key values where programmers, expert programmers, are just using flashes and barriers to write their code, which is running on existing hardware with very different ISA support. And most probably we will have different types of hardware in the future to optimize all those system support. And we don't want a tool for all, like different tool for all of them. We want to provide support with just one unifying tool. So in the tool that we have developed, PMTest, what we do is we want to provide fast and flexible support for testing. And for flexibility, let's assume we have this persistent program which is calling the PMDK library running on x86, or it could be a program using the Nemoseni library running on ARM, or it's just a kernel module which is basically using all the low-level primitives running on x86. So how can we provide some sort of interface to programmers which can cover all of those? And what we know is that at the end, consistency guarantee is providing two basic guarantees, ordering and durability, which is done using these low-level primitives. So what we do is we want to provide these, we want to test for just these two fundamental primitives, which should be hardware agnostic. And then maybe we can build up high-level testing mechanism on top of that. So in order to design a tool which is fast, let's first take a look at what existing tools do. So YAT is a tool from Intel where basically they take every possible combination of the writes and crash them and see if they can recover correctly or not. So basically, it's an n factorial number of combinations they have to test. And basically, it's just not practical. So what we want to do is we want to take a trace runtime and somehow infer all that information just using that trace. So it's a significant improvement from order factorial n, but the question is how to infer all possible combination from just one trace. So what we do is we introduce this notion of persistent interval, which basically says that what is the time interval when a write can become possibly persistent with any sort of reordering. So for this write, when we see the flash and barrier, that's where the interval ends. Similarly, some other writes can have other sort of interval. But if the intervals are disjoint, it means that there is no ordering where A will not persist before B. But if there is any overlap, that means that there is at least one ordering where A may not persist before B. And we use these analyses on persistent interval to infer that when the writes are possibly persisting. And we can query on the traces to say that if A did persist before B or not. So given these two key ideas, let's see how the interface and the background mechanism for PMTest looks like. So basically, PMTest has one offline stage and one online stage. In the offline, programmers annotate their code to say where they want to do their test. And in the online, basically, we just take the trace and check the trace using the rules that we have for different programming models. So first, let's take a look at the offline analysis. So we have two different interfaces, one for the expert programmers, which basically is more like assertions. So similar to assertions where programmers insert the assertions to figure out what's happening in the runtime if whatever is happening matches their expectation. This is very similar, like the programmers insert these checks, and at the runtime, the check either fails or passes. But it requires some understanding of the program. And for the regular programmers, we have a high-level interface where basically we are building on top of this low-level interface and automatically injecting this low-level interface to test the program. So for the low-level interface, there is just two checkers. They are corresponding to durability and ordering guarantee. So we only check if A is ordered before B, and we can check if a memory location has persisted or not. And basically, this helps us to check programs written in on these low-level primitives like flashes and barriers. So this is an example which is very similar to one of the PMDK examples for hashes. So basically, it's removing an element from the hash, and after that, the count is decremented. There is a barrier and some large portion of code in between before the hash map is rebuilt, which is an external function call. So the programmer, it's actually not that intuitive to know if a check has been persisted before the hash map is rebuilt. And also, we can just use is persisted to check if what happened within that hash map function, because the programmer may not want to actually go through that function to figure out what's happened. So the low-level interface, it kind of lets the programmers to reason about what the code is actually doing. And the other benefit is it's also enabling the high-level interface. So the high-level interface is basically related to the transactional library. And with the transaction begin and end, we just automatically inject the low-level checkers that we have and make sure that things that are supposed to be backed up are backed up. And if everything that has been updated within the transaction has been persisted. And we can also detect some performance bug if someone used too many flashes or logged the same thing twice. So at the end, high-level checkers are mostly automated, so it helps to, it reduces the burden on the programmers. So for the online part, basically, as I said, at the runtime, we have to say which portion of the code we need to check. And then basically, once we have the trace, we inject the low-level checkers, and the checking engine says if the checker failed or passed. And this one, I guess I will kind of skip. But basically, the checking engine, it's just looking at the persist interval. So for each write, if there is a write back, then the interval ends. If there is no write back, so for example, the second write to B, there is no matching write back to 8, so that interval never ended. So basically, if we ask that if A persists before, the intervals are overlapping, so no, they are not, it doesn't pass. If we ask if B persisted, there is no matching CLW for B, so no, it did not persist. So for the result, we have looked at some micro benchmarks from PMDK, and we also looked at some real-world workloads. And the baselines is the native performance compared to no tool, And also we compare it with Intel's PMMcheck, which is a Valgrind-based tool, and it can only test a subset of things which we are testing. So this is the result for micro benchmarks. In the x-axis, we have some trees and some hash maps, and in the y-axis, it's the speed up over PMMcheck. And basically, PMTest is 7 times faster than PMMcheck, but again, PMMcheck is Valgrind based. It's just slow. Like, and we are running, PMTest is integrated with the application. So this one is more interesting because here we are testing real-world workloads like memcached, Redis, persistent memory file system with different types of client. And what we see is PMTest has less than 2x overhead in these workloads. So it's pretty lightweight. And for Redis, which uses the PMDK library, that is actually 22x, it shows 22x slowdown if you just run with the native application. So we validated the tool with some synthetically generated bugs, and also we went through the repo for PMDK and reproduced some of their bugs that they have fixed. But we also found some new bugs. So one in PMDK application and some performance bugs where I guess it's not related to correctness. And we already reported it, it's all fixed, so it's fine. So to conclude, it is hard to guarantee crash consistency in persistent memory applications. And we have proposed this tool, open source tool PMTest, which is both fast and flexible. We just don't want to support existing application. It is flexible enough to adopt different type of transactions and persistent memory modeling. And it is fast enough. It incurs less than 2x overhead in real workloads. And we detected some new bugs in existing applications. So with that, I will conclude, and I am happy to take any questions.
So we've got about 2 minutes for questions. You finished right on time.
Yeah, so I have one observation and one question.
Yes.
So my observation is that this tool is kind of similar to how concurrency bugs are found.
Yes.
Because your persistence before is kind of similar to happens before.
Yeah.
So I was kind of wondering if there is some lessons to be taken from stuff like
so you're on spot. Like my student is right now working day and night on that project. So basically what we are saying is, if we think that the program that is running before failure, that's a thread, and the after recovery, that's the post-failure thread, they're racing for the same memory location, but it's just at different time.
Exactly.
And we can use that to detect where the error is happening. So here, the programmers still have to say that what type of, like, it's more like assertions, like it's not an automated testing tool. But with race detection, we can say, as long as we know that how the programming model works, what is persistent and what is what is consistent and what is not consistent, we can use that to detect bugs. Yes, that's a great question.
So I have also another question. Maybe. So when we developed PMTcheck, we didn't really concern ourselves about performance because it's a validation.
Yeah.
But the problem that you mentioned, that this really doesn't scale for big applications, because honestly, performance of PMTcheck, if we go exhaustive checking, pretty much it goes to infinity for complex applications. We literally ran a single test for a week because we wanted to have a comprehensive test of some of our critical data structures. And I don't think there is a way around that, honestly. We can instrument, like you show, some stuff, but I think exhaustive checking is the answer for some critical parts, and we do that for PMTK code itself. But my question or observation is that background is single-threaded, and it would be cool to have a tool that also has the same checking capabilities that could also check for correctness of concurrent multi-threaded applications, because that's a gap that PMCheck doesn't even cover that well.
Yes, so when we are doing this, we kind of say that, so we support multi-threaded application where there is no data race and when they are not sharing things, right? Which is basically not supporting multi-threaded at all. So yeah, I think it's an important problem to say that once there are concurrent multi-threaded workloads which are sharing data and updating them, and concurrently how to provide that support. I hear that some people are working on that, so maybe something will come up very recently.
I think it's reasonable to expect that if we run a persistent checker that the concurrency part is correct. Because, similarly, if you do memory sanitizing using Valgrind memcheck, then that's the basic stuff. You know, like you don't want to have a double free before you check if your concurrency is okay. So Valgrind, which is the Valgrind tool for checking concurrency patterns, expects the application to be correct in regards to memory stuff. And the same could be true, I think. It's reasonable to expect that persistent checkers could expect
that there is no data race, right?
Concurrency is correct.
Yeah.
But my point was more about having a checker that actually runs in multi-threaded applications.
Yeah. I understand what you mean. And I hear that like Jishan is already here. I hear that she's working on something. So hopefully we will see something. And I guess one comment I would make is actually if Intel provides us persistent cache as he was asking for, basically the problem actually marches to it becomes almost similar problem as data race, because anything is visible to the cache is now persistent. And in that case, most probably with just minor modification to data race tools, we could actually use those for persistent memory. So that actually would help, I guess, on the tool side.
Great, thanks.
Okay, yeah, thank you.